logic levels. So this is basic stuff. So I already talked about the for the slave side we have VIH from 0.9 to 3 volts, and then we have the minimum is 0.3, and the minus side minus 0.5 volts. And the master side, the pull-up voltage would be 2.8 volt maximum, and then the minimum or VOH would be 1.1 volt. So we have 200 millivolts between 0.9 and 1.1, and that's for a reason. Then we have to find the rising falling times. There's nothing special with them, so it's a pretty slow interface, but still we want to make sure that everything works. Protocol, so apologize again, busy page, but just main ideas in the protocol. So it's designed as data transfer interface, so it doesn't care about the data it transfers. Implementation, data for the protocol is not working, as I said. Can be implemented in software and hardware, and single master, not this way. Data rate, scalable from 2 kilobit per second to 250. Basically, speed is limited by slave receiver size configuration. Communication initiated always by the master, and is based on 17-bit data words with time distance coding. Communication speed is defined by the master always, and bit signaling is based on time distance coding. You will see that there. And then we support interrupts, password, first read write, slave power control, you and these words to name something. So the bit signal. So as I said, there are words here. So there's this is not full word, it's cut in the middle and just to make it shorter. There's word, and then there's always stop period. And base unit in bit is always tau bit. And tau bit can vary from 2 microseconds to 150 microseconds. And how the bits are coded, they are based on time between, so it should be easy and logical level. So when we have 0, it will be 1 tau bit before we change the state of the system. So here you see 0 first, so it will be 1 tau bit. And then we have 1 is 3 tau bit, so if it stays by 3 tau bits, it's 1, and so very simple. And after every word there is the stop period, which is at least 5 tau bit. And here are the details. Tau bit 0, 3 tau bit, stop, is 1, and 5 tau bit is stop. Stop is always hard. And then here are, you see 2 tau bits and 4 tau bit. These are to detect whether for the receiver side, how you would design the thresholds. So there's a good gap in the motion. Big word, so we have 17 bits, and it will start always with the training sequence. So training sequence sets the beat. So slave will listen to this sample, oversample this, and based on the time it comes here, it gets the speed with this training sequence. So there will be turn down, up, and then down again. And the training can be either 0, 1 or 1, 0. And it means whether we are sending unicast, multicast word or broadcast word. So that defines that. And then after the training sequence, we have a payload, 10 bits. And then parity bits, they are here, here, and here's the one. Four of them total. So the other is over here. And then inversion bit. So next, a little more about the details. So training sequence, it tells the slave the communication speed. So slave will answer at same speed always. So basically every transaction the host can send with certain speed the first transaction, but the next transaction could be 250 kilobits per second if the previous one was low speed. So every transaction is done with certain speed. So the training sequence purpose was to tell whether it was broadcast or multicast. Then the parity bits, so it compounds 15-bit coding. And PIP especially requires strong error detection because it's interface that the line can be cut. So you just drop your phone and it was communicating and you lose your data. If you don't have error detection, then you might have trouble. So that's why it was decided to have. And here are the rules how to calculate those parity bits. So the red ones, you count these bits and then it's even parity. Then the P2 would be, it's red. If this was uneven, then we would add 1 here to get it even. So that's different. And for the other parity bits, it's the same story. So there's P0 are green, P1 are gray, and so on. So inversion bits, as we know, the ones are 3 tau bits, and if all the bits were ones, we would have to really longer instead of short. So that's just to speed up. And the payload, so we have the 10-bit payload, and that's used with the PCF, so that's the broadcast flag, the training sequence. We define transactions, and there are 9 transactions defined, and we can say, for example, PC, VC is one command, so there are bits 10 to 8, they are the command, and then bit 7 to 0, sorry. This is coding the VC, and then we have the actual command. And also, next page, we have the commands. So we have defined 16 commands depending on how we count them, but then we have even range for manufacturer defined commands if you want to develop something fancy. And here are just example commands. So BUS would be 7, 8, 3rd, as we said, for example. And transaction examples. So first, for example, here we have a read transaction. So we have a device select. Then we would put the read address. Sorry, here, or read address. And this is read burst actually. And if you have selected the device, you can go for binary. So these are all defined in the spec. And here are more examples. So here is the master slave, and so on. So you would send these transactions this way. I will not go into detail. It takes pages to start to analyze this. So interrupt is one important feature in diff. It's working over the same line. So the master sends interrupt enable comment to the bus, and then the slaves they will go to the interrupt mode. And PCL line stays in interrupt mode until first interrupt pulse arrives. So it can stay in interrupt mode for days if there's no other traffic, if you like. And we have this big slave control function that can be used to generate interrupts. For example, temperature function can use slave control function to generate those periodically or then some thresholds. And then a protocol in the slave side. This is one important topic as well. So we have three modes: active, standby, and power down. And we have certain rules how to go from each state to other state. I will not go into details, but just to be honest, we have this many power modes. And then the slave data map. Key points in definition again. Compatibility with the MIPI. Of course, cost efficiency always. And the scalability meaning that you have to have some scalability. Manufacturability. So meaning programming support at different phases of battery. Slave battery pack production, and unified access, software access, write locking mechanism. That's actually a really important one. Manufacturer specific functions, boot, and 64 kilobytes memory address. So it's but there are ways to get easily. So this is just what would happen to the battery before it goes to the hands of the customer. So this is IC manufacturer line, battery pack manufacturer, mobile terminal manufacturer, and consumer. So first, mobile terminal manufacturer would have requirements to the battery pack manufacturer, and then battery pack manufacturer would have to IC manufacturer probably. Could be going straight also from the mobile terminal. Then IC manufacturer does the design, will program and lock certain things like unit ID, private keys if they have some authentication, certificates, whatever, and they will lock it. So the next guy on the chain, they cannot change any more this data.